Okay, so my name is Waleed, as you guys already know, and my topic is how deep learning AI can bring radical change to the medical field. So I'm going to first talk about just an overview of what deep learning is and how it differs from other machine learning, and then what kind of deep learning algorithms are used in the medical field today. So just to review, machine learning is basically when you have a program that changes its behavior depending on what kind of output you give it. So usually a machine learning model is given training data, which is labeled data that allows the model to determine what kind of characteristics in the data is assigned to what label. And then after given enough training data, it is given like actual data that is used in real life scenarios, and then it gives an output that's easily read by, let's say, a clinician or a researcher. So there are different classification models that machine learning can produce. So this classification model is basically created after reading training data and is used to assess future data that does not have any labels. So there's like single label versus multi-label, and there's also black box model, which is where the researcher or clinician is not able to read or understand how the algorithm actually gets to its output, compared to a transfer model where it's easily editable. And some examples of machine learning is cluster sampling, which is an unsupervised learning method. So unsupervised learning is, again, just when a machine learning algorithm is given unlabeled data, and then it just learns by itself how to appropriately label that data. Supervised learning with, let's say, k nearest neighbor, that is when it's given training data that's labeled as opposed to unlabeled, and then a clinician is able to assess the output, and it either tells the machine if the output is correct or incorrect. If it was incorrect, it would tell the machine that it was incorrect, and then the machine would then change its classification model to make sure that when characteristic within that data is given again, it would output the correct result. And then there's also neural networks, which is really my focus today. So deep learning, you can think of it as how neurons are arranged in the brain. You have a basic input layer, such as, let's say, your eyes or your ears, and those neurons, or AKA nodes in a deep learning algorithm, are connected to other nodes in a second layer. So as you can see here, you have the input layer in red, and each individual node is connected to the subsequent nodes in the hidden layer. And then you can have as many layers as you want. A simple neural network will just have one hidden layer. A deep will have like multiple, like 3 or maybe like 10. And what is the significance of having this layout? The main benefit of having this is that the accuracy of the resulting output is basically what happens is that the machine exhibits back propagation, which results in high accuracy outputs. So basically what that is that whenever, let's say, the clinician tells the machine it gave a wrong output. So basically what happens is that when you have, let's say, an input that goes through these two nodes, and then it goes through, let's say, these two nodes in the hidden layer, and then it goes through an output, and let's say the output is incorrect, so then it would change the weighting, which is a value assigned from 0 to 1. It changes the weighting on the nodes that are responsible for the output to make sure that the output is actually incorrect. So after multiple sequences of backpropagation, the output of the classification model is actually really accurate, and any type of input data given to a deep learning model can result in a highly accurate output. So how can this mechanism actually be used in a clinical environment? It's good to say, yeah, backpropagation does this, and deep learning is a type of machine learning, but how is it actually used? That is what I'm going to be talking about. So one one framework of a deep learning model used or is being researched is called Deep Patient, and this is basically a general diagnosing tool. So basically what researchers have discovered that when they take, let's say, clinical data of patients from a warehouse of patient data, which you can see in the top right. So let's say you have a database of clinical notes, diagnoses, medications, and then you take all of those data, you put them in deep learning, deep feature learning network, and it gives you the output of what the diagnosis for the patient is, like what type of medication the patient needs, what the patient has, and any possible future illnesses that they may have. And it's actually really user-friendly for clinicians because it just gives a simple output, like it just says, oh yeah, this patient has this, and it needs this and this, which is the main goal of deep patient or deep learning in general, is just it gives an easy to understand output. And this just shows the table which the study concluded to. So basically, these four here are other types of machine learning. K-means is comparable to K-nearest neighbor. And deep patient is the one that actually has the highest accuracy out of all of them. And raw feet is just analyzing the patient data without any type of machine-aided technology. And as you can see, 93% compared to the second highest, which is 89%. So clearly, the arrangement of nodes similar to neurons is allowing for a highly accurate diagnosis for patients. Another similar framework that is being studied is called DeepGene, which is used in classifying cancer cell types in patients with tumors. So basically what happens in this, it's just basically for all of the deep learning algorithms, or like how they're set up, basically they have a general similarity in that they have the neurons, but then some models differentiate between how they actually filter the raw data to make it more accurate, and then they put it through a DNN classifier. So what this does is that they take the raw gene data from the patient, specifically from the cells that are tumors, and then they go through two preliminary filtering steps known as clustering gene filtering and then indexed sparsity reducing. This one basically clusters the genetic mutations in the cells according to like similarity, and then it just continues to cluster them into like highly specified groups. And then this one basically rules out any genetic mutations that do not actually contribute to the rise of tumor cells. So this pre-filtering process actually narrows down the genetic data to the mutations that are solely responsible for the tumor in the patient. And then it is sent through a DNN classifier, and then the output is basically whether, like what types of cancer that the patient has throughout her body. And in all the studies, it is very important to, like, in order to assess how effective the DNN models actually are, you have to compare them to, let's say, raw data as well as other types of machine learning, just to have a comparable result for how deep learning networks are actually efficient. And so as you can see here, the DeepGene model is compared to SVM and KNN. KNN is K-nearest neighbors, and then SVM and NB are two other commonly used machine learning algorithms used in clinical environments today. So DeepGene, as you can see, has a 60% accuracy in classifying cancer cell types in patients, whereas SVM, KNN, and NB have less than 55%. And these results are actually the four models without using these two. So like all four models normally would use CGF and ISR, but to determine how reliable and accurate and precise the DNN classifier is by itself. They take both of these factors out of all four, and then they just assess how accurate the outputs are. So clearly, deep gene, just focusing on the neural network, it is about 5% accurate than the second highest, which is SVM. All right. So another one, another model that shows high potential for clinical use is a deep neural network that predicts type 2 diabetes in patients. And so how this works is that they take single nucleotide polymorphisms, SNPs, along with clinical data of the patients, and then they combine these two different data types into a single data with like a single vector, and then they input this into the deep neural network. And so clinical data, they take values such as patient's height, weight, family history, and then clinical values such as cholesterol, hypertension, and etc. And SNPs are basically single, as you can see here. Let's say you have 3 individuals with similar genome, and if you have a single base pair mutation or substitution, such as A turning into G or G turning into a T, that is basically what a single nucleotide polymorphism is. And again, the DNN output accuracy is compared to a linear model when it's given the same data. And yeah, so as you can see here, this is how the whole framework is set up. So you have the SNPs and the clinical factors entering the input layer, and then combining these, they go through 2 hidden layers, each with 50 nodes. So as I mentioned earlier, you can have as many nodes as you want with as many hidden layers as you want. Just depends on the limitations of your hardware. And tan H with dropout is just how it's a special tan function encoded in each node that differentiates whether the node, so like each node basically classifies or looks for a specific characteristics in the data, and each node uses the tan H with dropout to determine whether it detects the characteristic or not, and then it therefore travels down the network. And then the output layer is just whether there's diabetes or not. And this graph, it looks a little bit confusing, but it's actually not. So this is just the male results of the DNN, the deep learning network output compared to the linear regression, the linear model output. So the DNN results are from A to D, and the linear model is from E to G. And basically, the difference between the columns is that A and E is using 100 SNPs, B and F is using 200, C, G is using 400, D and H is using 700. So how you read this bar graph, basically, the x-axis is predicted risk, 1 being that the classification model predicts that there is diabetes, 0, no diabetes. But if you have anything in between, it means that the model is unsure whether the patient actually has diabetes or not. So as you can see here, in all graphs of the linear regression model, the model is actually highly inaccurate in determining whether the patient actually has diabetes or not. Over here, you can see that there's a lot of ambiguity in the output, whereas comparing to the deep neural network model, there is a lot more accuracy. Basically, the accuracy is how many outputs you have in the 0 and the 1, because you don't want anything in between, because that just shows that the model is inaccurate. And as you can see that as you increase the number of SNPs used, the DNN framework actually becomes more accurate. As you can see that there's a higher percentage of outputs in the yes and the no. Okay. Another method of detecting diabetes is through the same process called deep neural networks. And this basically detects for diabetic retinopathy, which is just a side effect of having diabetes that some patients have, which is like, I'll like explain in the next slide what it actually looks like. It's just like having hemorrhages and blood vessels pop in your eye. So basically how a deep neural network predicts diabetic retinopathy is it actually takes pictures of patients' eyes and it analyzes each pixel according to its color or light intensity. So then it detects whether there's like, let's say there's an aneurysm or a hemorrhage present in the picture. And the disease is classified according to its severeness. So there's moderate, worse, severe, or fully graded. And in the study that I'm talking about, they only take the fully graded results. And basically how they assess the DNN is through high sensitivity and high specificity testing. So basically what high sensitivity is how accurate the DNN is able to produce a positive, true positive, which is basically if the DNN, let's say the DNN predicts that 100 patients have diabetic retinopathy and 100 of them actually do have diabetic retinopathy, then the sensitivity of the DNN is 100%. Whereas high specificity, that focuses on whether it is able to differentiate between a patient that has retinopathy and a patient that doesn't. And yeah, so this is a normal retina where there's nothing wrong with it. And in diabetic retinopathy, you have some hemorrhages and aneurysms, and which causes complications in vision. So as you can see here, this is basically the results of a DNN classifier dependent on the number of training images it's given. So on the y-axis, the specificity is kept at 97%, and it's basically analyzing the sensitivity, which is how accurate the output is. And as you increase the number of images given in the training set, the sensitivity actually goes up and plateaus at around 100%, which indicates that as you give a deep neural network more training data, the accuracy actually increases. All right, so this can't all be good. There has to be some disadvantages and disadvantages. So what are some advantages? Well, as I've talked about numerous times, it's actually highly accurate when you're given enough training data. It can provide specific diagnosis, such as in the diabetic retinopathy classification. It could theoretically predict the different stages of the disease between like moderate or severe or fully graded, and this can allow for clinicians to actually give specified or highly personalized medicine depending on how severe the illness is and like how far along the disease is. And another advantage is that deep learning networks don't explicitly have to be told what type of characteristics it has to look for in data. It actually teaches itself because of backpropagation. Again, all the clinician or engineer, whoever's in charge of it, all they have to do is they have to, whenever there's an incorrect output during the training interval, it just has to correct the output, and then the model adjusts the note weightings accordingly. So what are the disadvantages? Basically, not a lot of diseases have a lot of data readily available. DNN actually requires like hundreds of thousands of training data in order to build an accurate classification model, which it can then use to predict for future data that is not labeled. The problem with diseases having low occurrences in the population is that let's say a disease has maybe 20 occurrences and 2 like different symptoms, and the DNN classifier builds a classification model based on just those 2 symptoms. And then let's say a new person has this disease and has a new symptom. the DNN classifier is obviously going to give an incorrect prediction because the classification model is not built on enough data, enough variation in the data. And as I talk about here, diseases with a wide range of symptoms or enough different types of symptoms is required for the deep learning model to accurately predict or analyze a picture. Let's say in diabetes retinopathy, it needs a lot of variation in diseases in order to accurately predict and assess clinical data. So what are the future uses of deep learning? So as you can probably speculate, deep learning can provide highly specialized treatments. This is because the DNN, like if it's given enough data, it can actually assess at what stage is the patient in its disease and what type of specialized treatments can the clinician provide. It can also give early diagnosis. So let's say a patient is showing early symptoms that, or maybe no symptoms at all, but let's say you do gene sequencing using machine learning, it could potentially detect the disease before it even shows any symptoms. So this can provide extremely early diagnosis and save a lot of money in treating the patient because the patient would not go through the whole process of having the extent of the disease normally, compared to if it's assessed through deep learning, then it's treated early and then less cost is used for the medicine. So what does this mean for the future of medicine? It can be debated whether deep learning can completely replace doctors. I don't think so. I think the ideal scenario would be a healthy balance between the two, because basically the main goal of deep learning, in my opinion, is that it saves time for clinicians, because scanning, like looking at a lot of MRIs and X-rays can be tiresome for a doctor's brain. And so feeding these through a deep neural network can save time for the clinician and allow for them to spend more time on perfecting the treatment actually given to the patient. So another question that can arise is that, okay, so it can predict diseases in patients, it can diagnose them, can it cure or treat them? Well, that is debatable. That comes with that is highly dependent on how medicine evolves in the future. Let's say medicine in the future, post-singularity, is able to cure uncurable diseases such as cancer. So if you combine this type of medicine with deep learning, you can diagnose cancer early in, let's say, like a 2-year-old or like infant years. You can actually cure the cancer before it even shows harmful symptoms. However, all of these deep neural network models are not actually used in any hospital setting because of the big limitation of needing huge amounts of training data. However, if in the future, if we have enough occurrences of pretty much all diseases, theoretically, you can use deep learning for almost all diagnoses, and it can like radically change how hospitals and doctors diagnose medicine or diagnose diseases. Any questions? Yeah.
So you had a bar graph a few slides ago. Can you flip back to it? It's pretty early on.
That one?
No, keep going.
Okay. This one?
That one.
Okay.
So you said that gene has a 60% accuracy of classifying cancer cells or cell types and stuff. So how accurate are humans in doing this?
Don't actually know. So all of my papers, they basically compared the deep neural network with other machine learning. They didn't really focus on how accurate humans are, because it's assumed that machine learning can do it more efficiently because it can process larger amounts of data than humans. So it basically compares what kind of machine learning. It narrows down on machine learning and which one's the best, basically. And all of my papers say that when you use neural networks, it actually produces a more accurate result in less time. Yep.
Also, besides the need for large amounts of training data, what do you think are other obstacles to the implementation of these machine learning algorithms in a clinical setting?
I think that, like Caesar talked about, hardware is another big factor that will affect the development of deep learning in the future because, well, theoretically, you can have as many hidden layers and nodes as you want, but that computing power is highly dependent on how capable the hardware is in processing the data. So that really depends. And deep learning, it doesn't actually happen in like milliseconds or seconds. It still takes time. So even though it's accurate, it still takes time, but it's still faster than the other machine learning. So honestly, like, let's say post-singularity, you have infinitely exponential growth in computational power. Theoretically, if the software development of deep learning also keeps up with that, you can theoretically like have like an infinitely accurate deep learning model that can be used in any diagnosis.
Other questions?
Yeah.
So we looked at AI specifically and how deep learning affects how accurate they can be. Is this the only, is AI one-dimensional when it comes to deep learning? Because you mentioned that they can provide data which is accurate, and it continues to be accurate as they keep getting developed. But is that the only stage where they'll be at? Will they only be used for analysis? Will they be able to make their own choices to later down the line instead of using clinicians to make that choice? Or will they just guide them in the right direction?
Yeah, I think that is so basically what you're talking about is whether an AI with deep learning is going to replace doctors.
Is that possible?
Yeah, so that could be a possibility. It all depends on well, whether doctors will be useful. So basically, what is the profession of a doctor? Is it just to diagnose? Is it to provide empathy for the patient? Can computers even provide empathy? Or can computers actually provide empathy later in the future, and therefore, is there actually no use for doctors? I think that's a possible scenario. Because I think this is all recent stuff within the last, let's say, 5 years at maximum. I think at this rate, deep learning will exponentially grow in its use. And I think maybe eventually it will start to be used clinically worldwide. And I think there's a possibility that it will start to maybe not completely remove doctors from hospitals, maybe partially, maybe like if you go in a walk-in clinic, maybe there's a computer that you just input all your data and then it just gives you like a diagnosis of what you have. Like you just have like a common cold. That could happen. I could see that happening. Yeah.
So let me give you an example. So humans are in charge of a vehicle and they drive it, and there's a debate behind the ethics of self-driving cars on whether or not, if say a car accident occurs, what they prioritize in terms of life. In a similar sense, when a physician misdiagnoses a disease, for example, and provides the incorrect treatment that may harm harm the patient.
Yeah.
The physician is more or less, I guess, shielded from any potential ramifications because that's what they've done. So, relating back to your deep learning algorithms, is there any security involved with these so that there's no threat to the potential diagnosis that these computer programs may provide to patients? Because if it's something along those lines and patient data is exposed and incorrect treatments are given,
yeah,
there can be a big risk of patient life.
Yeah, I can see how that is probably one of the other main reasons why this isn't actually used yet. But as they develop this, it can be more accurate, and it can lessen the error in diagnosing it and giving suggested medication. However, according to accountability, as you were saying, I think that would probably result in doctors not being completely removed, because I think that doctors would, in the end, need to have the final call, so that there has to be some accountability for what is happening to the patient, because you can't just have like a computer diagnosing a patient, and then if something was wrong, well, whose fault is it? It's really hard to tell. Is it the developer's fault or is it the computer's fault? That is like a really serious ethical question for the future.
So
Yeah.
Since you said that deep learning is dependent on the volume of data you have for a particular disease that you're diagnosing, right?
Yeah.
So with like diabetes and diabetic retinopathy, there's like so much, I don't know, like clinical help that you get these days with maybe like nurses training you, or there's diabetic clinics, endocrinologists, and like dietitians and stuff. That we're controlling the condition far better now than we were before, and not like the rates at which like previous rates of diabetic retinopathy occurring are much lower today. So if we don't have enough data, certain things just won't be developed. If it's just like that's the hinge point that it stops at, or can we create like mock data and train them with that?
I think mock data is a possibility, but like you still have to make sure like the mock data, is it like accurate? Like you're just not making symptoms up. I think that even with several hundred sets of data, it's still relatively accurate, maybe equivalent to other machine learning models. Regarding whether you can actually, if you can amplify data from diseases that have low occurrences, I think that at this point, I'd say that the basis of deep learning is that it needs large training data. Maybe in the future, it can actually operate on low training data, which can allow for this to be used more readily. But currently, I'd say that it's restricted to just diagnosing and predicting common illnesses. Yeah.
Related to that, do you think it's a significant barrier then to having the technology in developing countries or third world countries? Like, can you collect data that applies, like that allows you to apply deep learning all around the world, or is it going to be limited to the places where you can collect the most data?
That's a good question. I think that well, that all depends on how accessible the data is. So let's say the government of one country collects data on one illness, but doesn't want to release it on a public domain. That means that country is able to use deep learning for that disease, but then others won't. So it all depends on how accessible the data is. I think that in the future, like as the internet grows, more and more information is being uploaded online and being easily accessible by anyone who just has an internet connection. So I think that as long as enough documented cases of diseases are recorded and they're online, deep learning network can function anywhere. Yeah.
So do you think that these, essentially this is software, and software is a very lucrative industry, so do you think there's competing companies, this would increase or decrease the cost of healthcare diagnostics and healthcare as a whole? Do you think that nations with more privatized healthcare systems, such as the United States, would be more readily to accept these, I guess, not necessarily clinically, like these more experimental, methods of machine learning in diagnostics compared to more public systems such as Canada? So do you think, in short, it will drive down cost or increase cost for developed nations?
I think, yeah, so regarding the development in, let's say, the US, in like a highly privatized country, I think that it will see it will be developed in privatized countries first, because they have the money to actually research and develop this, because the organization and creation of the deep neural network, it's actually harder than other machine learning, because the engineer has to figure out in what arrangement does the nodes have to connect, and what type of classification and what type of characteristics each node has to code for. So so I think different private companies will develop their own variation of deep learning, and then these would increase the cost. Whereas I think later, after highly commercialized countries such as US, after they've developed it, I think that countries such as Canada that are more focused on providing the same commodity to everyone, I think that they would get this technology second, and then I think that the third world countries, they would get it last after, because like third world countries, I think that they will also, their technology is accelerating at the same rate. They're just like lagging behind. So like for example, like we've had purified water in our countries for several hundred years at least. Third world countries are just getting that now. So like they're still advancing, they're just like several steps behind. So I think that everyone will have them. It's just a matter of who has the money and who is able to develop it first. Yeah.
So initially during a diagnosis, you have to have a clinician who has some sort of hunch to what it might be, to then input into this neural network, whether it's a biopsy or a blood test. Do you think there will come a point where the need for that initial clinician will be gone?
Yeah, I think so. Because so initially, how a deep neural network actually learns is that it's given label data, which is already predetermined data, and it's classified. Like let's say it's an image of cancer cells, and it's already labeled like what type of cancer it is, and then it's fed through the network, and then it is the model is set to give an output that gives the same output as what the original data is labeled. So if it's given enough data initially, like let's say thousands and millions, it doesn't really need anyone to correct its output when it's given unlabeled data, because the classification model is so accurate, because it's given so many data, different types of data, that is highly unlikely that an incorrect output is actually given. So yeah, it's possible that eventually, as this technology is developed, there's no need for anyone to actually double check. But then that also arises the question, what if there is a mistake? Who is responsible for that?
What I meant more was, do you think you'll be able to walk into a hospital and say, I don't feel well, I've been having chest pain? And do you think the machine will know where to go from there? Or do you think the clinician who's going to say, okay, maybe you're having a heart attack, or maybe you have this type of cancer, so we have to do a biopsy and then we'll give it to this machine?
Okay, I see what you're saying. So I think, from my understanding, what the clinician basically does is that, they take like a bunch of readings from the patient, like let's say heart rate and breathing rate and cholesterol or other clinical measurements. So theoretically, machines could do the same thing, and then the machines could input the data into a deep learning. And basically, I think a deep neural network is like analogous to a doctor in the sense that it gives a diagnosis. So if you, let's say you replace the doctor's purpose of predicting what's wrong with the patient, you can replace that with just taking, I see a bunch of scenarios. You can either have machines take measurements from the patient and then input that data into the network, and then it gives a diagnosis, or you can just the clinician cannot make any hunch. It can take all possible clinical measurements as it can, and then just inputs all of them into a deep neural network, and then based on the classification model, it just analyzes patterns based on the data, and it compares it to the previously labeled training data, and then it gives a diagnosis.
So we're discussing both of these presentations as if medicine was all science and not art. Like you can imagine that an experienced clinician you can tell from like the way the patient looks, the color of their skin, the way they walk, the way they hold their body, a whole bunch of things like that. So it is more nuanced, and the health of the patient is related to the health of society, and the way the societies run, and all that kind of thing. But still, AI could master all those things ultimately. That doesn't mean that physicians will still have a big role in 100 years. It just means that we need to consider this a bit more broadly than just pure science of identifying the individual disease in the individual patient. I think that machines might be just as capable of figuring out this other stuff. How a patient walks and looks, and how their skin appears. Might be more sensitive to various things there than human beings ultimately are. Can also analyze society and governmental systems and tell us what's wrong there. So those things are all somehow connected. But I don't think it assures us that there's some component that will always remain human, that machines cannot ever approach.
Yeah, it's all dependent on how advanced AI becomes in the future. Are they able to replace aspects of humans that we think that are not replaceable, such as emotion and detecting like body language? Like, will machines be able to produce emotions? Are they able to feel empathy with patients? Are they able to have a hunch? Well, that is all based on how they develop in the future.
See, there's a kind of machine intelligence we don't think about. That's lie detectors. They've been around for a long time, right? They aren't all that accurate, but you can imagine that if that increases quite a lot, that also has a place here in figuring out which human beings are telling the truth, and which inputs the machine is receiving should be trusted inputs. So in general, that's also an important part of the overall challenge.
Yeah. And I also think that in the past, there have been symptoms and diseases that were considered witchcraft. Like clinicians would have no idea why this is happening in the patient, but then now they found the genetic causes and the physical, psychological causes for those symptoms. So maybe in the future, AI is able to actually convert, let's say, body language that might not seem on the surface a scientific concept, but maybe in the future we might find a scientific explanation for body language, or maybe emotion. We might actually find how emotions actually work, and we can actually replicate them in machines. So that's another possibility.
Yeah, even the problem of free will, as we sit here and think about planning things, you can also ask the question, can we actually plan anything, or is everything just playing out according to physics, and we just think we have some influence? So that's even something, machines can help us solve that. Can tell us whether there is actually free will, and do we have it? Do they have it? Where does it rest? Okay, thank you very much, and I look forward to